Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand how to interpret position graphs for various objects. So, let me explain kind of what we're looking at here. I've got this picture here, and for this discussion we're going to imagine this automobile here, and don't worry about what it's doing right now. A position graph is the graph of the position of the object, here represented by, I put X here, with respect to time. Now, you can represent position with any variable you want. This is going to be a one-dimensional example, and I'm going to choose X to represent the position of an object. Now, before you can start graphing it, the first thing you have to do is actually define what X is. So let me open a new photo, or a new picture that I have saved for you folks. Oops. Okay, so typically, when you're studying the motion of an object, in this case, we're going to talk about this car, the first thing you would do is maybe put in a set of coordinates, a Cartesian coordinate system like this. Now, even though this is going to be a one-dimensional example, I tend to use two-dimensional sets of coordinates because it's probably one of the most common. Like if you're taking a college physics class, you'll see lots of two-dimensional examples. But in this example, as this car goes down the road, only its x coordinate is going to be changing because it's not going to be moving up or down. It also doesn't matter where we put the origin here. I put it right behind the car, but I could put it lower down if I want, up here if I want, over on the right if I want. It also does not matter which way we define as positive. I could put this pointing the other way if I wished, but I just want to keep this video as simple as I can. In most cases, I think people are generally used to seeing right positive on coordinate systems like this. So the position of the car is described by its x coordinate, which I basically put in red here. Now we're going to chat a little bit about what a graph of position versus time would look like. So if we call x the position of the car, then what we'd be plotting would be x on the vertical axis, probably in meters, but it could be in centimeters or kilometers or feet or miles or any given distance. However, the gold standard in physics is the meter. And time, usually we would put in seconds. Now, where the zero is doesn't really matter either. I just plopped a zero right here in this little Cartesian grid here. And then the intent of this graph is to be able to describe where the car is at any given time. All right, so let me pull up a picture of what the next graph might look like. I'm going to start with this one. Okay, so here is a position graph that's describing the position of this car. Now, you'll notice that this line is horizontal. And if I were to look at some values here, like when t is 0, x is, let's see, 1, 2, 3, 4, 5 meters. And if I come over here to say 1, 2, 3, I don't know, t equals 4 seconds, and we read the x coordinate, 1, 2, 3, 4, 5 meters. And you notice that no matter where I am on the axis, no matter what time I choose on the horizontal axis, I'm going to get x equals 5 meters. And what that's demonstrating is that this car is not moving. Now, just some kind of what ifs. Had the car been sitting at the coordinate system origin, this graph would look identical, except the horizontal line would be here, along here at x equals 0. Or had the car been sitting over maybe to the left, say 2 meters, then this graph would have started down here and again been perfectly horizontal. Now, when you're dealing with graphs, a very important concept is slope. And remember, slope is rise over run. And you'll notice that the slope of this line anywhere is 0. Pick any 2 points on that line, calculate a slope, you're going to get 0 because the rise is going to be a delta x, and there is no delta x for this car. And again, I'm going to save the discussion about slope a little in more detail for another video. Let me move on with this. Again, highlight here, if position versus time is horizontal like this, the car's not moving, or whatever object we're talking about. Oops. Okay, let's look at maybe a case something like this. All right, so here's another potential graph that describes the motion of this car. Now, You notice this one ends up being basically linear, at least to within my hand drawing here. Now, intercepts are always important. At t equals 0, the x-coordinate of that car is, let's see, 1, 2, 3, 4, 5 meters, meaning at t equals 0, the car is 5 meters to the right of this origin. Now, you'll notice if we go, say, maybe 2 seconds later, 1, 2, now the car is at 1, 2, 3, 4, 5, well, just short of 6. Humor me, let me call that 6. So the car now has moved over to x equals 6, meaning this distance has increased. And this car has moved over here somewhere. And you notice that basically every second that goes by, now if I start here on the graph, a second goes by, x got a little bit bigger. Second goes by, x got a little bit bigger. Second goes by, x got a little bit bigger. As the car, or as time goes on, the x coordinate's getting larger, indicating that this car is moving. Now, let's talk a little bit about slope. You'll notice the slope is positive. The positive slope is indicating that x is getting larger. And because x is pointing to the right, that's actually telling us the direction that the car is moving. That car is moving to the right. And also notice that the slope is not changing. So the slope represents, the rate that the car is moving. For now, let me just call that speed, and I'll get in, more detail about this in my next set of videos about it. But this constant slope, right, that's positive, is indicating that the car is moving in what we're calling the positive direction. I've got x right is positive, and the rate at which it's moving is not changing. So when an object's moving at constant speed, the slope of your position graph here, this thing will stay straight. Now, what I just said here, I use the term speed, and you can have constant speeds where, how do I want to put this? I can have one like this and another one that has the same steepness and have the same speed, but have different slopes, one being plus and one being minus, and that has to do with the difference between speed and what's called velocity, but I'm going to save that discussion for another video. This is just meant to be kind of an introductory video. So for now, it's good enough to say that our slope is not changing. So the rate at which this car is moving is not changing. For every, let's say, looks like roughly about 2 seconds, the car is moving about a meter. 2 more seconds, car moves another meter. A little less maybe than a meter, but 2 seconds, car moves about a meter. It's probably about what, maybe 0.8. And again, notice 2 seconds goes by, car goes another 0.8 or so meters. 2 seconds, car moves another 0.8 or so meters. And again, this car is moving to the right because of the positive slope. Let me bring up another example here. Which one was next here? Okay. So here's another potential graph here that describes the motion of this car. Now, a very important thing to realize here, we'll do this in blue. If we look in this region right here, you notice in that region the x-coordinate on the left is basically 5, and on the right it's also 5. So the car, in this region, not moving. Okay, so right here, in this region here, this car is sitting still. And again, you'll notice that the slope of that line of the graph is about 0. But notice now, look at, say, a region over here. Maybe use a different color here. Green. Look at this region. The time went from 1, 2, 3, 4, 5, roughly 6, and the x-coordinate 1, 2, 3, 4, 5, roughly 6. 2, let's see, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7. So in this 3-second time frame, the car moved, about a meter. Now, you'll notice here that if I picked a couple points here, let me put those in red, like here and here. And if I draw a line through them, I get a line with a positive slope. And again, that positive slope is indicating that that car is moving to the right. And again, I'm going to save what that slope is called for another video here. For now, our position graph has some slope. Car's moving to the right. Also notice the slope is positive. That means that that X is increasing and the car, again, moving to the right. And let's look at a couple more points. And let me use a different color here. Oh, let's use this. That's a pretty color. Let's look at like this region here. And I'll go ahead and use red again. And we look at these 2 points and draw a line. So some important things about this graph. Within the blue region, the average slope, if you will, in this area is 0. Car's not moving. In this circled region, the slope of the line between these 2 points is some number, and it's roughly looking at it, let's see, we're over 3 up about 1. It's roughly around 0.3. I'm getting that from 1 over about 3, meaning that the car is moving about 0.3 meter per second in this region. And in this region here, let's see, we're going up maybe 1, 2 for over 1, 2, 3, we're moving at about 0.6 meter per second. So again, you want to think in terms of slope, and notice that the slope is 0, car's not moving. Slope is a small positive number, car's moving relatively slowly to the right. Slope is a larger positive number, that's indicating that the car is moving even faster, and again, still moving to the right because of the positive slope there. All right, let me pull up another graph. All right, third example I want to talk about in this video. All right, so here's a position graph against time. And we'll look at this first time frame here, just this region right here. And again, you'll notice that if I pick a point like here and here, and I draw what's called the tangent line, you notice that the tangent line is relatively steep. In fact, if I actually calculated the slope, let's see, it's 1, 2, 3 over, 3 up, 2 over. The slope is around 1.5 meter per second. The slope is positive, indicating this car is moving to the right. Or you could think of it like this. X is getting bigger. Right, so over here, this X is getting bigger. Again, car moving to the right. Now, look at the next, or another time frame. Like, let's take a look at this time frame right here. And again, notice that I'm just going to pick a couple points here and draw the tangent line through them. Notice that the slope has decreased. It is still positive, meaning the car is still going to the right. Or you can think about it like this. The X value here and here, the second one is bigger, meaning this is increasing. So again, car's moving to the right. But you'll notice that the steepness is considerably less than the first one, right? So this car is not moving quite as fast in this blue region as it was in the green. This car is in fact slowing down. And in fact, let's talk about the a third region here. Look at this region right here. Now I just kind of sketched this by hand, but if I pick a point here and draw in the tangent line, you notice it has a slope of 0. So this car, it's not moving at this point. Notice the X coordinate here at this time and this time, they're the same number. This thing doesn't change in those intervals. So that car was moving to the right reasonably fast in this green region. In this blue region, it had slowed down considerably. And here in this kind of pinkish region on the graph, the car's not moving at all. So this would indicate a car that was originally moving to the right, but slowed to rest. So the purpose of this video is just to go through examples of how to interpret these position graphs. I think I'm going to end this video here. It's getting a little on the long side. I hope that this has helped you understand these position graphs a little bit better. Have a great day.